So, the next part of our study would be norms and normed vector spaces. Now, the mathematical concept of associating the length of a vector is basically called a norm. I mean, if you think about a metric for anything, for example, if you think about the measure of your milk, right, it is a liter or a gallon or some few cups, whatever that cup measure is for you, right, there is a metric, there is always a quantity that you associate with things. So, similarly we have the notion of associating some metric to vectors. So, the mathematical concept of associating with the length of a vector this is basically the norm, and this concept is useful later when we deal with inner products and so on. So, we will first come to the definition of what this norm is, right. Let S be a vector space with elements x, some x, right, it is just some variable here. A real valued function denoted within these double bars is said to be the norm of x if the following conditions so they hold, right. So, let us see what those conditions are. Norm of x is greater than or equal to 0 for any x. So, this is a vector. So, sometimes I miss these bars down, but I think you should be savvy enough in the class to figure out that this is indeed a vector and not a scalar for any x belonging to this space. So, I think this should be making some sense for us, right. I mean, this is a definition. I mean, there is no reason philosophically to rote learn these definitions at all, because these come from we formulate things, we understand, we fix things, and then we figure out a clear way of defining these quantities. So, one may think from pedagogical reasons that you go with definitions. Of course, we go with definitions, then we write our lemmas and theorems and so on and so forth, but it could be also the other way around, that you are interested in solving a problem, you figure out what to solve the problem, fix all the conditions towards the integrity of the solution, and that then formulate your definitions, what have to be done to define these things this way. So, I said length, right, length of a vector being negative makes no sense. It is like age of a individual is negative, it makes no sense, right. but maybe in a bank account your credit or debit, right, it can be positive, negative, that there is a notion of negativity and positivity. Here if I say length being negative 5 meters is absurd, right. So therefore the norm has to be greater than or equal to 0, right. 0 if it is, basically we will come to that point here, norm of x is equal to 0 if and only if x is basically 0, it is a null. If it is a null, then this length is basically 0, else it has some length. Then norm of alpha x is some alpha times norm of x, and x can be a complex, means alpha can be a complex quantity as well. So therefore you have to bring in this notion of the absolute length, and norm of x plus y is less than or equal to norm of x plus norm of y. This is the triangle inequality that we know for vectors, right, and this is basically to prove this you can invoke the Pythagorean theorem. This is length x, length y, this is length x plus y. So there are some interesting properties one can prove, and we will do this as a part of homeworks, the parallelogram property, etc., Apollonius theorem, etc., that you have studied in your high school, they can be brought out to apply here for vectors. So we'll see this through homeworks. Now along with this notion of norm, there are various other definitions or metrics for your normed norm spaces. And how do you define this norm? I said norm is some real valued function is what it is. What sort of real valued function is it? These are questions which naturally come into our mind. What sort of functions can we define, right? And that gives us various definitions and metrics. The first is the L1 norm, and this is denoted as this quantity here, which is basically summa I equal to 1 to n. Assume that we have n such coordinates for this vector, right. Again this is a vector, here an underscore. So take the absolute on each coordinate, sum them up, and this is what you get. This is the L1 norm or L1 distance. So if you just generalize this, we have the LP norm, which is denoted as x P norm, so which is basically summa I equals 1 to n absolute value of xi power p, sum them up over all the n coordinates, take the pth root of it. And you would have seen this in the context of the in the L2, where you have to define the square root of x square plus y square, right. You would have seen this quantity in some way or the other. So and trivially for the L2 norm p equals to 2, and then this is basically what we have. So, in general we can define an LP norm which is what we have. Now, we do this, we get to the L infinity norm, which is basically maximum over I equals 1 to dot 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 till n absolute value of xi. So, these are the definitions, right. Look at all the coordinates, absolute value of that, maximum over that is the L infinity norm. Now, I think it is very important for us to think how these norms are related geometrically, because if you think about the geometry, it is very easy for you to visualize and picture where this vector lies, what is the boundary, what are we trying to optimize, and that picture becomes very, very clear. So, let us see the shapes in R2. That means, we have all our vectors which are in R2, that is 2 coordinates, 2 dimensional vectors, and we want to see where these norms reside. My rhombus is not exactly up to mark. So, if I look at the L1 norm to be less than or equal to 1, right, all the vectors should lie inside this rhombus, right. So, this is basically modulus of x plus modulus, this basically implies modulus of x1, right, plus modulus of x2 is less than or equal to 1. We need to satisfy this equation. So, my rhombus is not perfectly rhombus. So, the way it looks here, so I think you have to bear with me that these angles are all 90 degrees, right. This is modulus of x1 plus modulus of x2 is less than or equal to 1. Now, you draw the boundaries for this and you will end up with this geometric shape. So, if the L1 norm is less than or equal to 1, which means that you have all these 2 dimensional vectors which are lying inside this rhombus. So, let us see what L2 does for us. Suppose I want the condition that my L2 norm of x is less than or equal to 1, right. So, which means that when I take mod x1 square, it is basically x1 square, right, plus x2 square is less than or equal to, I take the square root and that has to be less than 1, I mean I just could write a square root here, right, that is less than or equal to 1, square both sides, you will have x1 square plus x2 square is less than or equal to 1, and we trivially know that x1 square plus x2 square equal to 1 is basically a circle, right, centered at the origin. This is from our basic coordinate geometry. So, all our 2 dimensional vectors are lying inside this circle. Clear? This is the geometry. So, when we are saying that we are constrained now to set of vectors in L1 and we want to optimize in L1 or optimize in L2, that means we should think about this geometry. This is where the vectors are lying inside this boundary, and we are constraining it to this space, and we are doing some things on that, right. And what norm should you choose for what problem? It is up to you and up to the problem to decide. So, optimization typically is there is many ways. I mean, it is subjective and really depends upon what your objective is really. Now, similar to this L1 and L2, we also have the L infinity norm, and this is again not so difficult. You have to use this definition that L infinity norm is maximum over all the coordinates the length of xi. So, basically it would just be, if I say norm L infinity is less than or equal to 1, you can imagine that your maximum over absolute of x1 or absolute of x2, right. You can't go above this wall here or go beyond this wall here, so on and so forth, right. Everything is inside this. Clear? So, this gives you sort of a picture what the various norms are for vectors. Clear? The geometry is very important. I think one is the math, the equation, the definition for that metric, but you have to get the geometry into your mind, where exactly in what space, in which geometric shape these vectors lie, and that is very important. And once you are able to translate it to that point, it is easier for you to see the picture. Now, what we have for vectors, we can do this for functions. Signals are also functions of time, right. We can do this for functions. So, similarly, for functions, defined over this interval a b, this is a closed interval, we can define these norms as follows. L1 is basically take the modulus of x of t, integrate it from a to b, and that is your L1 norm for this function. And I am sure now you can recall when you learnt your Fourier conditions. So, absolute summability, etc., what is this definition, and here you see this in this sense. For LP, so, it is basically pth root of this. So, at every point in the signal, basically you take the absolute value, right, you raise it to the power, then you integrate it, that is basically you accumulate all these positive quantities and take the pth root of this, and that is what the meaning is of this LP norm. And if p equals 2, you are looking at the square signal, this is square integrability in some sense. Clear? We have not gone to signals, yes, we are only talking about functions, but this is like a signal. So, we have the L infinity notion, and this is soup. Is a superior value of the absolute value of x of t over this interval a to b, right. So, you might not exactly get the maximum value, and therefore, you have superior, because in the it is the tightest upper bound that you can get to this quantity. I mean, you want the maximum of this, you can't exactly get maximum, you have a sequence of bounds that you want, and you want the tightest bound to x t, modulus of x t, and that is the meaning of this superior, and this is of course for 1 less than or equal to p less than infinity. Okay. We have a definition, a vector x is normalized if norm of x equal to 1. So, I think it is trivial to say that it is possible to normalize any vector except the 0 vector, because you know 0 vector you can't normalize it, you can't divide by 0, right. So, and x over norm of x is basically the unit vector, because you take the norm of x over norm x, the length is 1 trivially, because norm x is a scalar, you pull it out, then you have norm x over norm x cancels out, right. So, you have to be careful now when people just write norm straightforward, you have to ask which norm, in what sense, at least that ability you should have to question in what sense is your definition, or in what sense is your notion of length, right, and according to that you have to think whether it is working out or not. Well, I mean, we have to put these underscores because it is a vector. So, with this we are ready to look into inner product spaces. So, I will define what an inner product space is, and then we can look into some of these results in the inner product spaces. Let S be a vector space defined over a scalar field R an inner product function is basically a function from S to S, the Cartesian product of this vector space. That means I should take two vectors, right. I mean S to S means it is a Cartesian product, and from this it is a function from S to S to R with the following properties. X y, the inner product, so you can have these vectors which are all reals, or they can be having coordinates that are complex numbers, right. So, inner product of x y is basically the inner product y x complement for the complex case, else you can say x y inner product is basically y x. We have the second property, alpha x with y. So, we can assume without much loss of generality, we just consider the reals, right, for all the coordinates. So, if you take alpha x with y, take the inner product, it is basically alpha times the inner product with x and y. For every alpha belonging to real numbers. So, there is the third property which is basically distributive. You take x plus y and take the inner product with z, this is basically x z, inner product of x z with, and then inner product with y and z, right. This is basically distributive property, and we have the last property which is the inner product of x with itself, because now this is basically the Cartesian product of the vector space, right. I can pull another vector y to be x itself, and I take the inner product of x with x, and that is greater than 0 for all x not equal to 0 and 0 even only if x is basically this null vector, right. If all these conditions are satisfied, then this is basically the inner product function. So, it has to satisfy all these properties. It has to be noted in this definition, we are considering this inner product function as basically a function which is operating over the Cartesian product of this vector space to the set of all real numbers. And when I gave this property IP1 saying that this is the inner product of x y is basically yx conjugated, and this is for complex. I mean, you think about this definition, this is applicable to reals, and this is where you have to focus upon x y. The inner product of x y is basically the inner product of y with x, and this is the property which holds. I just mentioned complex just as an aside. So, if we define this inner product function to be a complex function that happens in some applications in the area in quantum information or in various other applications, then we may have to modify and tweak some of these definitions slightly differently. Now, suppose I think about the inner product of x and y, right. So, I have x to be some x1 so on till xn, and some y is this vector y is basically coordinates y1 till yn, right. So, the inner product of x and y is basically x transpose y, right. It is x1 y1 plus x2 y2 plus so on till xn yn, and this is basically y transpose x. For vectors whose entries are all real numbers, if they have complex entries, there are some more trivialities which we will reserve it for homeworks.